We begin this second class with the continuation of the study of physical quantities and vector algebra. Today we are going to address the law of homogeneity to continue with the previous class. We are going to address a little bit better how we arrive at the total definition of the units that appear in the different systems of units. We will always try to focus on the international convention that exists in the international system of units. Of course, we are going to see what they are for and how to work with the equations of dimensions that will give us in the end the definition and the sense of the law of homogeneity. We saw in the previous presentation that the international system of units is defined starting from 7 fundamental magnitudes, 2 supplementary magnitudes, and the defining equations that allow us to obtain the different derived quantities. And also, some examples with their own names of derived quantities and how the different physical systems appear according to the type of unit. Quantities that we choose for each of the systems of units with which we want to work. We are going to see an example of how we arrive at the final definition of one of the units we have. For instance, within the field of mechanics, among the physical quantities we have to work with, we have length, mass, and time. In the international system of units, these physical quantities are represented by the meter, kilogram, and second. Well, the last definition, because it has undergone different evolutions, the definition of the meter, the last definition, as I said, that we have of the meter dates from 1983. And in the end, the definition with which we have to work is always included in the different conventions of the general conferences on weights and measures. In particular, this final definition of the meter was addressed in conference number 17 and is documented exactly as such in the official State Gazette of April 30th, 1994. In the end, the definition currently adopted for the meter is the length of the path traveled in a vacuum by light during a 1-second interval, which is a surprisingly large quantity, almost 300 million meters. Why this quantity? Well, this has to do with the fact that the speed of light in a vacuum is exactly those almost 300 million meters per second. This is how the different units are defined in order to have clear patterns with which we have to compare. We have done this for the meter. We can do the same and look in the official gazettes of the state for the units of mass, for the units of time, kilograms, second, etc., for the rest of physical magnitudes that we have. Among the supplementary units, we said that we had 2, since there was no global agreement on whether to include them in fundamental units or in derivatives. These supplementary quantities are the case of the plane angle and the solid angle. The plane angle, which I think is familiar to all of us, could be defined from the plane angle, that having its vertices at the center of the circle intercepts on the circumference of that circle, an arc related to the radius. The drawing is quite explanatory, and the relation between what would be the angle, the arc, and the radius that I use is given to me by this algebraic expression. The units are radians. And we have the relationship between what they would be. So what would correspond to a sexagesimal degree with radians, or a radian with the sexagesimal degrees? The other magnitude is the solid angle, which would be the idea of the plane angle, but extended to the 3 dimensions. I will work in this case with a solid angle that depends on the section intercepted by the sphere divided by the radius squared. And in that case, the units we work with are the steradians. Now, to see a little bit how to express the derived quantities in terms of the fundamental quantities, and to see if my physical laws expressed algebraically are correct, we use, and we are going to use very much, what are defined as the dimensional equations. What are the dimensional equations? Well, what the dimensional equations express are the magnitudes derived as a function of the fundamental ones, to know which fundamental magnitudes depend on them. Of course, we have to keep in mind that they are symbolic equations, they are not physical equations, and they do not relate the quantities of the magnitudes. This example already appeared in the previous class. We approach it now with more detail. Here, acceleration is expressed as a function of velocity and time. Could we say that acceleration, which is a derived quantity for the international system, is expressed this way in terms of fundamental quantities? No. Is velocity not a fundamental quantity? Time is, but velocity isn't. Should we, if we want the total relationship in terms of fundamental quantities, express velocity as a function of what? Of length. And time as well, right? But we would also have, in this other expression, the acceleration in terms of the second derivative of the position vector with respect to time squared. Could we say that this relationship is indeed a derived quantity in terms of fundamentals? That is correct. We would have length and time in the denominator. Therefore, in this case, yes. Another case of relationship, but with two derived quantities. We would have acceleration as a function of force, which is not fundamental, and mass, which is fundamental. But if we wanted to, we could do the dimensional analysis and see on which fundamental quantities the force depends. We will see this later in an example. All these equations, if we want to check if they are or correspond to physical laws, we are going to have to demand that they necessarily comply with what we know as the law of homogeneity. This law tells me that in every physical equation, both members must be homogeneous with respect to all the fundamental magnitudes. We have to have the same dimensions, therefore. Let's analyze this example. Here we have J shooting a triple to his basket in a basketball game. I am asked, analyzing the velocity of the ball at each instant, we have been told that the dependence of that velocity is, according to this expression, V equals. And in the numerator, I have H, P, and in the denominator, G, M subscript, P, and T. And here I have defined all the variables of this dependence. That is, the height of the ball above the ground, the weight of the ball, the acceleration of gravity, the mass of the ball, and the time elapsed since the throw. Can this expression here really define the velocity of the ball at a given instant of time? Well, one way to know if this expression is correct is to do the dimensional analysis. If we do the dimensional analysis of this expression, we have to take into account that in the numerator we had h, p, and in the denominator g, m sub p, and t. H, units of length, p, units of mass per unit length divided by square of time, times g, which is units of length per length squared, mass, units or dimensions of mass, and time, units of time, logically. If we simplify what we have in the numerator and in the denominator, we have length divided by time squared. Length divided by time squared would simplify this mass with this mass, and nothing else would be simplified. I can simplify all these terms because I have them all in the numerator and in the denominator. Then what do I have left? Length divided by time, dimensions in the second term. The dimensions in the first term are length divided by time. So in fact, this expression that I was given in the statement does correspond to the expression of velocity. Reviewing, therefore, everything we have dealt with in this class, what we have done has been to determine and explain how we arrive at the end to define the standard with which we are going to compare the different physical quantities, their units, and how they are expressed. We have seen how the law of homogeneity is defined, and, in the end, the importance of equality of dimensions in any physical law. We will continue in the next class with the analysis of vector algebra. With all the mathematical concepts that we need for this course, they will be very useful. Thank you very much.